Hi, thank you for your time. My name is Yuanhang Qiu, come from Meiji University. Now I'm going to talk about our paper submitted to Interspeech 2020. The title of our paper is Adversarial Latent Representation Learning for Speech Enhancement. This is the outline of my presentation. I'll give you a brief introduction, including background, related work, and the motivation of our work and the first. And then I will introduce the details of our model, our experiments and results. And at the end, the conclusions of this work is presented as well. Here is the introduction part. As everyone knows, speech enhancement is one of the most important speech signal processing technology. It aims to improve the quality and intelligibility of the degraded speech or said contaminated speech. It has a wider range of applications in real life. For example, speech enhancement is usually applied in telephone communications, in hearing aid devices, and nowadays it is often used in smart dialogue devices. So with different enhancement purposes, different application scenarios, kinds of speech enhancement approaches are proposed, from the traditional methods for stationary noise reduction to the deep learning methods for complex reverberation reduction. The speech enhancement is developed greatly, but the aim to get higher quality and intelligibility speech is always the same. Here in this work, we focus on deep generative models for single-channel speech enhancement. Previously, the traditional digital signal processing methods performed well in stationary noise reduction, but the performance of these methods is not satisfactory in more complex scenarios with assorted interference. Along with noise reduction, the serious speech degradation happens generally. But the advent of data-driven deep models alleviate these problems significantly. The main contributions of deep model methods, such as the effective information mapping, the representation learning, have attracted much attention and demonstrated a huge potential in complex speech signal processing. And some effective training tricks, like the adversarial training mechanism of generative adversarial networks, can further improve the model's training processing and information learning effectively. Here, we present a basic speech enhancement framework based on conditional generative adversarial network. Initially, the generator takes in noisy speech and a latent vector as input samples. In practice, a random noisy distribution is selected as latent vector. The discriminator is assigned to judge if the generated distribution is more similar to the clean speech distribution. And it has also been proven that the adversarial training mechanism indeed improved the speech representation learning and clean speech utterance generation effectively. Since then, more and more modifications were proposed based on this framework to explore the game-based speech enhancement. But to the best of my knowledge, no attention has been paid to latent space and explore its impact on representation learning in speech enhancement area. Actually, there has been some works exploring related data space for information learning in image processing, for example, InfoGAN, DeepSeek. And these methods indicate that it is possible that the latent vectors are used by the generator in a highly entangled way. That will cause the individual dimensions of latent vectors to not correspond to features of the data, or that the generative adversarial network may ignore much of the useful information. Hence, we focus on latent space information learning and try to propose a new model to alleviate this weakness and improve speech enhancement. Inspired by the mentioned work above, we hypothesize that the latent space may contain useful information that can be used for further representation learning. Based on that, we propose adversarial latent representation learning methods tending to explore the impact of latent information on speech enhancement. Next, I want to introduce the details of our method. In order to excavate more effective speech representation, an extra encoder is developed based on the conditional game framework. The encoder tends to learn an inverse mapping from the generated distribution to the latent space. The inverse learning methods builds an interconnection between the generator and the encoder that ensures the generated samples is able to capture the latent information and improve speech representation learning. To accomplish this mapping, a new loss function is proposed combined with relativistic loss function. Our method keeps a time domain end-to-end architecture that can take in raw speech waveform and output clean speech directly. For generator, the downsampling and then upsampling architecture seems to be the most suitable framework to learn the speech representation and reconstruct it without interference. Our generator applies two dimensions convolution layers and followed by parametric ReLU activation function, and the latent vector is concatenated with the bottleneck layers representation. One of the important effects is explained that to achieve the information compensation. In addition, the skip connection is used to alleviate information loss problem and can also make the gradients flow deeper through the whole structure. These operations can alleviate the gradients vanish and improve the effectiveness of model training greatly. Different with generator, the discriminator takes generated samples and raw clean speech as input. Another difference is the discriminator adopts virtual batch normalizations followed by leaky ReLU activation function. The architecture is effective to learn discriminable information for real or fake judgment of the input source. As a preliminary trial, we developed the encoder referring to the structure of discriminator, but removed the final fully connected layer to match the dimension of random noise. In particular, we apply multi-head self-rotation mechanism to learn the long-range dependencies and improve inverse mapping from the generated distribution to the latent space. So the whole framework of our methods can be roughly presented like this. We take a generator for clean speech generation, discriminator for real or fake judgments, and the encoder for latent information excavation. We keep the adversarial training to update the whole model simultaneously. The experimental results demonstrated that our method is effective and outperforms the baseline. The details of experiments and results. In this work, we evaluate our methods with a popular open resource from Edinburgh Dataset. The basic information is shown here. There are 13 speakers in total, including 15 females and 15 male speakers. The entire duration is about 20 hours. The noisy types and signal-to-noisy ratio in training set and test set are all different. This indicates that the dataset is credible for speech enhancement performance evaluation. Here is the evaluation results of our method in speech quality and intelligibility. We also evaluate the methods in different signal-to-noise ratio to explore the further performance. Comparing with two game-based methods, as we can see, our method shows the best performance over them in average evaluation. Especially, we also found that our methods performed better in low signal-to-noise ratio scenarios. Here, we also present several examples of the enhanced speech with different signal-to-noise ratio scenarios. Let's try to perceive the difference.
Again, we were lucky. Again, we were lucky. They took a risk. They took a risk. That's the truth. That's the truth. The service from the other players was super. The service from the other players was super.
With the effective enhancement performance, we concluded that the latent information is useful for speech representation learning, and the proposed encoder is feasible to excavate latent information. Our adversarial latent representation learning methods is effective to improve speech enhancement. That's all. Thank you for your time.